Today's lecture is about wired LANs and Ethernet. IEEE Project 802. In 1985, the IEEE Computer Society started the 802 project. This project sets standards to enable intercommunication among equipment from a variety of manufacturers. I think we already mentioned why this is important, because when you follow a standard, then different manufacturer can produce hardware or that will work or comply to each other, so that you can interconnect different hardware because they use the same standards. These standards specify functions of major LAN protocols of physical and data link layers. So the scope of this project is both physical and data link layer. Okay, so the 802 project deals with data link and physical layer specifications. The upper layers not included in this project. As we said before, this layer is subdivided into two sublayers: the logic link control sublayer and the MAC sublayer. We studied many of these protocols last lecture, media access control or MAC layer. IEEE also created several physical layer standards for different LAN protocols. So they are together with these MAC protocols, there are different physical layer standards that we'll study in this lecture. So IEEE actually has working groups, has got several working groups. The currently active working groups are these ones. I highlighted two of them that we'll study. So 802.3 is the Ethernet working group, which releases standards for the Ethernet, and 802.11 is wireless LAN working group, which releases standards for wireless updates standards for wireless area networks. There are different other standards. For example, 802.15 is for personal area network, or WPANs, wireless personal area network. There is also 802.18, 802.19. These are all active groups. There are many non-active groups also, but I just mentioned these ones and highlighted these two that will study these standards in more detail. So if you can, if you want, you can check on the internet. I just 1 second. You see, this is the IEEE 802 page, and if you see the working groups, Here are the active working groups. Okay, so 802.3 deals with Ethernet, 11 deals with wireless LAN. So if you open this, for example, you see all the different standards related to these working groups, and 802.11 that we'll study. So all the activities of the group, you can see them here. The standards released, the different activities. So as we said, we'll study the Ethernet in this lecture. Ethernet actually has evolved from slow, you can say nowadays, 10 megabit per second to up to very fast 10 gigabit per second versions available now. So it started with a standard Ethernet, then came the fast Ethernet at 100 megabit per second, then the gigabit Ethernet, which works at 1 gigabit per second, and then came the 10 gigabit Ethernet, which works at 10 gigabit per second. The Ethernet frame format, this is important to that you know different fields in this frame. Ethernet does not provide any mechanism for acknowledging received frames. Okay, so when you send a frame, you don't know if it's delivered or not. There is no acknowledgement, making it what is known unreliable medium. So it's unreliable. Acknowledgement must be implemented at higher layers, like the transmission control protocol or application layer protocol. So reliability is not a function of Ethernet, it's a function of upper layer protocols. So let's see what is in this frame, the standard Ethernet frame. We have 7 bytes for preamble. We'll study them in the next slides. And then we have the 1 byte for start frame delimiter. Then we have 6 bytes for destination address, and then another 6 bytes for source address. So what type of addresses these are? Who can tell me? What type of addresses? Okay, we'll come to that next slides. Length or type, which is 2 bytes in size, and this is the actual data that you want to send. And sometimes you need padding because, as we said, we have size limits, minimum size limits for Ethernet protocols, if you remember. Therefore, if the minimum payload, if the payload is less than this, you need to add some padding to make it at least 46 bytes. This is important for the Ethernet to work because we have constraints on frame size for Ethernet protocol, for carrier cells multiple access collision detection protocol, if you remember in the previous lectures. And then comes CRC. CRC means it's a redundancy check. So can check if the data is delivered properly or not. Okay, so let's study one by one. Preamble is the first field of the 802.3 frame. Okay, so all Ethernet standards use this frame format. This is important to know. Okay, the preamble is the first field and contains 7 bytes. 7 times 8 is 56 bits of alternating zeros and 1 that alerts the receiving system to the coming frame and enables it to synchronize its input timing. The preamble is actually added at the physical layer. Okay, so this is important to synchronize the sender and receiver, that clocks, because if you don't know the beginning of a 0 or a beginning of 1, it's hard to decode the data. So synchronization is very important. The preamble its main purpose is to synchronize the receiving and sending systems. Start frame delimiter field is 1 byte. This is the format. So it's 10101011. Signals the beginning of the frame. So when you receive this one, you know that the frame will start. The SFD warns the station or stations that this is the last chance for synchronization. If the receiving station cannot use or cannot synchronize using the preamble, then this is the chance, because these are alternating bits again, you see. So there is a chance here also for the receivers to synchronize with the sender. So if they can't synchronize, then they will receive the data and process it. If they can't, then they cannot process the data. The last 2 bits is 11 and alerts the receiver that the next field is the destination address. So because exactly after this, the destination address will come. Destination address is 6 byte. As you remember, we spoke about physical addresses or MAC addresses. So this is a MAC address. MAC addresses consist of 6 bytes. For example, 6 bytes. We have hexadecimal digits. So if we 1, 2, 3, 4, 5, 6. These 3 bytes, we have actually half of it for the manufacturer and the other half is just a number. So actually we don't have any 2 devices with the same MAC numbers. Okay, so if you we showed you how to get your the MAC address of your device. For example, you can just go in the command line and then type get MAC. It will give you the MAC address, or you can, for example, this is mine. I can wait. So this is my MAC address. You see, 6 bytes, 1 byte, 2 bytes, 3, 4, 5, 6. If you look at this, I'm not sure what's the manufacturer of my, but this is related to the manufacturer. So if you have a device from the same manufacturer, then this part will be the same. Okay, the other part is just a number. So we don't have any two devices with the same MAC address. They should be different always. So physical address is a MAC address. It's 6 bytes. And we have source address. It's also physical address of the source of the sender. It's also 6 bytes and contains the physical address of the sender. Length or type, length of the frame or type of the data. Data field is the actual data that you want to send. Its length is minimum and maximum. So you have this data can be a minimum of this 46 and a maximum of, so if you have more data than this 1500 bytes, you cannot send it in one Ethernet frame. You have to create another frame to send that. If you have, for example, 100 or 1500 or 2, then you make, this is one frame maximum, and then put the other two in another frame. But the other frame, its minimum size is 46. So you have 2 of data and plus 42 padding. This padding is just, 44 padding. This padding is just to make the frame size acceptable minimum. Because if you exceed this minimum, if your frame is less than this minimum size, then the Ethernet may not work properly, because we have restrictions on frame size, minimum frame size. CRC stands for cyclic redundancy check, which contains error detection information. So when you send the frame, sometimes errors may happen, and then the receiver should be able to check if the frame is delivered properly or not. If it contains error, maybe the upper layers then will ask for the frame to be resent. So if we go back to the implementations, standard Ethernet uses one persistent, as we studied, carrier sense multiple access collision detection. The standard Ethernet defines several physical layers. So we have many physical layer implementations. So if we come, so we are now talking about the standard Ethernet. Standard Ethernet works. It's almost obsolete now. We don't see standard Ethernets, but the concepts are the same. So standard Ethernet uses one persistent carrier sense multiple access collision detection. And physical layer implementations, we have different implementations. 10 base 5. You see, 10 is for data rate. Base means baseband transmission, and 5 means it's actually 500 meters. That's the distance. We have 10 base 2. We'll see the details in the next slides. And we have 10 base T. T means twisted pair. So it can be UTP or STP. We don't usually use STP with the standard Ethernet. And we have 10 base F, F for fiber. These are these actually were common implementations. Nowadays you will rarely see Ethernet, standard Ethernet, because the standard is almost now the 1 gigabit Ethernet. So we are not going to concentrate much on these standards. So in 10 base 5, you see it's called thick Ethernet. The cable, coaxial cable, is normally thicker than the normal one that you see we use for example, satellite. When you connect the satellite with the LNB, that's normal thin Ethernet. This one is thicker. We use here bus topology. So this is a bus topology. You have to use terminal and or terminators to prevent, of course, reflections. And when you need a device, you need these T connectors, as we studied before. The length is about 500 meters, so this 5 came from this one. We have the 10 base 2, which is called thin Ethernet. It still works at 10 megabit per second. It's baseband, and the distance is nearly 200 meters. So again, it's bus topology. You need, if you want to connect a device, you need these T connectors, and to terminate, you need these matching terminators. So if the resistance is or impedance is 50 ohm, so this should terminate in 50 ohm. We have the more common twisted pair, 10 base T. So 10 means 10 megabit baseband, and T twisted pair. We actually here use a star topology instead of the bus. So we have a hub, or it can be a switch. Normally it was a hub, and the switches were not very common at that time. So you normally have a hub, and then connect the devices using the UTP cables with the RJ45 connectors that you studied. The maximum length of these segments cannot be more than 100 meters. So these segments, any of them, can not be more than, so it's the maximum in the standard, okay, is 100 meter. So again, this is for baseband, megabits per second, which is 10 baseband signal, and then digit twisted pair. Uh, 10 base F means is fiber, 10 megabit per second baseband fiber. Baseband means there is no modulation. Baseband communication, we don't have modulation. You studied baseband and you studied different modulation techniques. There are several of fiber 10 megabit per second Ethernet, but 10 base F is the most common. Actually, was the most common. It uses a star topology. So again, you have a hub and you have the devices. You see, we have sender fiber and receiver fiber. For each device, you have two fibers, one for sending, one for receiving. So we connect them in a star topology, physical star topology. I explained this before. So the physical address is actually 6 bytes or 12 hexa digits, which equals 12 times because you see, it's 12 hexadigits, which equals 48 bits. Okay, so each of these are, this is 1 byte. Okay, 4 bits, 4 times 12, which equals 48 bits. The first you see, the first half is for the manufacturer. We study the multicast and unicast. If the this bit here is 1, it's multicast frame. If this bit is 0, is a unicast. We study the coming lectures. Bridge and collision domains. By collision domains, we mean that collision can happen in between any of these devices, so they are in one collision domain. So if this one sends a frame, can collide with a frame sent by this one or by this one or by any of these. So any of these are all in a single collision domain. So without a bridge, all these devices are using or sharing the same media, and they will be in a single collision domain. Of course, when the devices and the number of devices increase, the possibility of collisions increase. So the performance of the network will also decrease, because there will be more collisions. When a collision happens, you need to resend that data, because the data will be damaged. So it's not practical to have large collision, many numbers of a device in one collision domain. Therefore, we normally separate these into several collision domains. How we separate? We can use bridges. So a bridge can, if you put a bridge here, then there will be two separate collision domains. Okay, so if, as we said, if there are many collisions, then the actual data rate, so even if it's 10 megabit per second, but because there are so many collisions, the actual data rate can be lower than that. So the average send may get to 5 megabit per second. This is if you have two devices, but if you have 10 devices, then it will even go lower to 1 megabit per second, and so on. So when the number of devices increase in one collision domain, the actual data rate will decrease and the performance will decrease. So we normally subdivide them into different collision domains, and we use bridges. So in this case, we put a bridge here. Okay, then the collision domain is now separated into two collision domains.